Good afternoon, ladies and gentlemen. It's a pleasure to be invited. I'd like to thank the Physiological Society for asking me back. It's also a great pleasure to talk to you about this topic, which is one that has become a passion with me. In my professional career, I saw what I think was the evolution of statistical use, the use of statistics in medicine. When I shifted to be on the editorial board of the of the Journal of Physiology, and I was surprised to realize that basic scientists hadn't evolved at the same rate as medicine. And they were still in what isn't quite the Stone Age, you could almost call it the Rothamsted era of statistical analysis. This is a shame because a large number of books are available to tell you how to do statistics properly, to explain statistics, even at the level that I understand statistics, which is what I call hand-waving, thinking of things and just sort of chattering about it. I don't do equations, and you'll be glad to know there should be no equations in this presentation. A lot of journals recognize this as well, and they would like to know that the statistics in the articles that they publish have these characteristics. But a large number of them, many of them, fall short, unfortunately. Who's responsible? Well, a whole variety of people, but the authors obviously are partly responsible for this. Statistics is not a technical tool, it's a discipline. You need to understand the principles of it. You don't necessarily need to know exactly how a pH meter works, but you do need to understand the background, the bottom line in statistical tests. And a lot of people relegate it to the minor. They've spent a lot of time doing their experiment, and then they think they can rattle off the statistics by squirting them into a bit of software and getting the result out. There are lots of problems, but the main one is orthodoxy. So much so that there have been articles written by psychologists on why people can't change the way they think about these things. There's no free thinking. You just keep on doing what the Romans did, what your boss tells you to do. You don't think freely enough. And part of that comes, of course, from the worry that if your article doesn't look like the other articles that are published in that journal, you're going to get ridiculed or rejected. But the answer is to understand what's going on so that we can avoid the error of parading behind someone with no clothes and end up being unclothed ourselves as well. The other problems that I've noticed are the preoccupation with p-values and the misapplication of statistics, often when they're not necessary. There's also a problem which I think lay people find, that is non-statisticians find, is that there is a jargon, there is a specialized vocabulary there, which when a statistician uses a word, it means as much or as little as he wants it to mean, and it doesn't really have a lot of relationship to what you see, the way you see the word being used in everyday parlance. The other problem is going on using the wrong old tools for the job and not recognizing the fact that modern statistics have developed new methods to deal with laboratory science. Old-fashioned statistics were not really designed to deal with stuff from laboratories. So understanding what's going on and a better toolbox of tests would be the cure for this problem. In clinical trials, I spent some of my time working on the Committee of Safety of Medicines, which has now become the Medicines and Healthcare Regulatory Authority. There was often one simple, single question. Is treatment A better than treatment B? And under those circumstances, what was called the Neyman-Pearson rule of setting a confidence limit of 1 in 20 so that you didn't make a mistake very often with the statistical test was acceptable. But that's not what happens in basic science. Here we've got evolving hypotheses that have to be explored and tested in a more subtle and nuanced way. And Fisher's original idea of using the p-value as a help to other methods and measures that we had in our experimental results was much more sensible thing to do. So I'm going to go on now and talk about some practical applications and try to make some recommendations for how to change things. The first thing is the data have to be shown, not concealed. We all know that a picture is worth 1,000 words. I would say a plot is worth a paragraph. It will give you all the information about, for example, experimental design in a single picture. The other thing is to make those pictures as simple as possible. And the concept of the data-ink ratio was put forward by Edward Tufte in his books, magnificent books, real cult books, and I recommend them to you. He had an example in one of his books where he showed this absolutely awful graphic that was being used by NASA when they were analysing the failures of their booster rockets. They did have the sense to put with this picture the following comment, that you shouldn't try to understand it unless someone explained it to you first. Well, that's not a good picture then, it is. It's not a good plot. If you actually go back and look at that, you can see there are some of these diagrams of rockets have little marks on them. Those are the failures, and that's really what needs to be analysed. And the best analysis that you should be doing here is to looking at, they're Americans of course, so it's degrees Fahrenheit here. This is the temperature of the launching site, and these were the failures. Not much of a signal there, but if you add in the successes, you can see there's a bit of an idea coming out that the low temperature isn't very healthy, and that was disastrously proved in January 1986 when they launched a rocket with an ambient temperature down there, and 7 astronauts died shortly after takeoff. So, present the data clearly, and to do that, show it in a visual form. Most of you will only have small samples, and you can easily plot individual values. And don't try to conceal variation. The standard error of the mean is the standard way, sorry about the pun, of doing that, because it gives the smallest scatter, but it's not a really good measure of things. I'll come back to that in a moment. So here's someone that's produced what I call a dynamite plunger plot. The only two bits of information that are important here are the mean and the little bar on top which says the standard error. Conceals more than it reveals. Let's look at what really it should look like. Here we have an n of 50. Here we've taken a subset of these values and only produced 6, taken at random from these original 50 data here. And you can see that we've concealed successfully the fact that these are a skewed distribution, possibly logarithmic. Maybe someone's been taking percentages or ratios or something like that, and they often become skewed like that. And we can also see that if we take a very small sample, we really, even when we show the dot plot, don't get a very good idea of the distribution, merely because we've randomly sampled only a few values. So, if you show all the data as dots, then you may pick up the fact you've got a single population, maybe you've got 2 populations, or maybe you've got an outlier which is altering your data. Dot plots are a good quality control device. I've mentioned the first 3 of these things already. The fourth, the measure of precision and dispersion, I'm going to touch on now. Here we have that 50 samples again with a mean and the standard deviation. a perfectly satisfactory way of indicating the scatter of the values in the population. Might be better if you use the 95% confidence intervals, which will encompass all the values in the population, but of course you can transform a standard deviation into a 95 confidence interval very easily. The standard error of the mean, on the other hand, which is tiny here because we've got a large number of samples, is merely a measure of the precision with which you have quantified the mean of the sample. It's not a good indication of the scatter. Better, if you want to quantify the precision, is to use the 95% confidence intervals of the mean value. And you can see that in the subsample, we get different ratios between these different measures because these values, the standard error, depends upon the number in the sample. Here, there's a smaller number in the sample, and the standard error is very large. So, going back to some of the original problems, one of the problems is lack of understanding and what I call p-worship. Nothing's allowed to be written in a paper sometimes without a p dangling from it. What is a p-value? Well, you may remember it's something to do with the null hypothesis. And the idea is that you have to disprove it. If you do disprove it, and this p-value would normally be accepted as disproving it, what does that mean? And these are all possible explanations that were put in front of a statistical audience, and not many of them got the right answer. I'm not going to ask you to come up with the right answer. I'm going to go back to the basics and talk about what the null hypothesis exactly is. We've done an experiment. We've got a sample which we presume has come from a larger population. And this figure is a sort of oblique reference to the inventor of the t-test, student, who worked for the Guinness brewery and was interested in keeping a constant quality of barley coming into the factory. So he was taking small samples from the sacks, and he wanted to know whether this was different from that. If you wanted to know whether they were different, you actually turn the question on its head and you say, could they be the same? Could those two samples have come from the same bag? So you forget where the samples have really come from, and you suggest that they could have come from the same bag, the same samples, that these two samples could have come from the same theoretical population here, which is a mixture of all of those things. In fact, it's not. You have to derive what that theoretical population could be if you had these two samples, which of course is all you do have. So what's the probability of finding this and this if your samples have been taken at random from this single theoretical population? And we use these samples to estimate the features of this population. So here's a worked example, if you like. In these samples here, there are 2,500 points. Makes it a big slide actually on the computer, but there are 2,500 points in both of those. It's the normally distributed. It's got a standard deviation of 1, and this population has got a mean of 0.5, whereas this population has got a mean. That's a mean of 1. That's got a mean of 0. And for our experiment, we take from these large samples, large enough really almost to be population, which in theory is infinitely incised, and we take a sample of 10 from the black ones and a sample of 10 from the grey ones once. Then we put those back and take another random sample. We put those back and take another random sample. And you can see that by using a sample size of 10 in each group, we get p-values that dot about all over the place. So the p-value is here a very variable number. Let's look at this in practice now, and I'm moving away from the theory and coming to practical assessment and evaluation of data. And I stole this from a paper somewhere, I'm not going to tell you where because I'd embarrass the authors. They were looking at 2 different hospitals. They studied 45 patients from this one and 44 patients from that one, so fairly matched and relatively large study sample sizes. And here we have 3 p-values that I'm going to consider. First of all, this one, 0.72, not significant, but let's look a little bit more closely. First of all, is the null hypothesis tenable? Not really. They've come from different hospitals, and there might be lots and lots of confounding factors rather than and how you can in any way argue that there's a null under these circumstances is fairly limited. The other problem is that if you look at the mean and standard deviation here, it doesn't make any sense at all. You've got a mean of 0.31. Well, what is 0.31 of a tablet? People don't get given tablets in thirds. And the standard deviation is 1.3. What that means is that if it were a normal distribution like that, that would be where 0 would be. That would be about 0.38. And some of the patients would be producing tablets, not consuming them. Not possible. So trying to force that into a t-test is an absolute bit of nonsense and shouldn't be done. What in reality would happen is, of course, that most patients would get no tablets, some would get 1, and if you were lucky, you might get 2. Let's look at morphine now. Exactly the same argument here applies. 6.7 mean quantity with a standard deviation of 12.4, again implying that some patients were producing morphine rather than receiving it. And again, that's because they were getting injections of 10 milligrams, and most of them didn't get any. Some of them would get 1 injection, some of them might get 2. This was given in a different fashion, and again, almost certainly was a skewed distribution of intravenous administration of morphine. So that means nothing. It's the wrong test to use under the circumstances. In fact, you probably really shouldn't test that at all. Let's look at something which should be normally distributed, the PCO2 in the patients, and there was a highly statistically significant difference, but the difference, in fact, is small. It's smaller than the standard deviation, so it's probably clinically trivial under those circumstances. And finally, let's move to what is the really important message of this study, which was respiratory depression. Here we've got a difference in frequency of 17.8 compared with 9.1. 45 people in this group, 44 in that group. Not significant, but I personally would be a little bit worried about that number if it were my, let's say my grandmother was in this hospital, in this hospital compared with that one. How do we analyze those data? Well, I'm sure many of you will know that this is a sort of chi-squared test or something like it, maybe Fisher's exact test, although Fisher designed his study with very tight limits on it and probably shouldn't be used for this sort of thing. What I've mentioned here are what are called the marginal values. They allow you to interpret the test properly and work out what you'd expect to find. So we add up those and we add up those that way, and we produce the marginal values round that contingency table. 45 patients in this hospital, 8 of them got respiratory depression. 44 patients in this hospital, 3 got respiratory depression. So if there were no difference, then you'd expect to see 11 out of 89 not getting respiratory depression. I'm sorry, those are the depressed patients. So because these groups are roughly the same, you'd have thought there should be 5 here and maybe 5 or 6 there, or maybe the other way around. But these numbers are sufficiently close to 5, both of them, to mean that the value is not significant. You need a bigger sample. Now, the next step it has to be taken with a health warning because you can't extrapolate these things immediately. But if you doubled the sample size to 90 and 88, and you didn't change these ratios of depression to total, then you would get a highly significant value. Now that's not necessarily what's going to happen because these are individual events, and maybe you just, let's say you added 8 or 9 patients to the sample size, that would boot up the number of depressions by 1, and it might have been added to this group rather than that group. Whatever, remember that you need larger samples to get more reliable results. A better way of expressing that sort of problem is of the risk ratio. The relative risk ratio is 2.6 to 1. The confidence intervals have just been exceeded. So in fact, that's an even better measure. Even though that p-value is significant, it could be no difference or virtually no difference between these two hospitals. So here we come to the idea of power now. What is the point of looking for differences when you can't necessarily be certain that a negative value doesn't establish the opposite? What I put in one of the articles we wrote in the Journal of Physiology is this little sort of catchphrase, not different is not the same as the same. Failing to disprove the null hypothesis does not mean to say that you've been able to show no difference. It merely means you've not done a powerful enough study, usually, to show it. If you went on forever studying very large populations, you'd always find a difference. Always find a difference, because all random samples are random, and there might be just a purely random difference. The other thing is that, particularly in medicine, but also possibly in other sciences, this question of if nothing goes wrong, is everything all right? You can't say something's safe if you've done it 20 times and there's not been a problem. But there's still a substantial likelihood that you've just not got a large enough sample to find a problem. Just to bang on about the unreliability of p-values for a moment or two. This was my sample that I showed you before, 2,500 values. This is another one, slightly different, with mean value slightly different, slightly shifted, if you like, along this axis. The mean differs here by 0.05, the SD is 0.1, and if you do a t-test using all those numbers, you get a satisfactorily small p-value because you've got a nice big sample size. However, most of us don't have the luxury of being able to get samples of 2,500 values. We're down to scrabbling around, taking little random samples from these two populations and trying to see if there's a difference. So there is a difference when the whole populations are tested, but in our small samples, what do we find? We find that the p-value dots around all over the place. That's the magic p-value of 0.05. And in successive tests, we find the p-value goes up and down because we haven't got enough samples to adequately characterize the population. These are the last 4 of those shown as distribution histograms. So that's the distribution of values in the sample we took compared with that distribution. Exactly the same number of samples, but because they're small, they vary around. So this one, that gives a p of 0.5, that gives a p of 0.11, that gives a p of 0.02. So a lot of variation. The power of the test depends upon how large the effect you're looking for. It could be that you'd be happy with samples that large if these populations were in a different place. This one is shifted much more away from the mean of that one. It depends how much variation there is in the population, in other words, the tightness of this distribution, and it depends how large the sample you take is. The downside of taking small samples, apart from not often having a powerful enough test, is that if you do get a powerful enough test, what you find is that you've exaggerated, or you've by chance picked a pair of samples that exaggerate the effect. So this is the 95 confidence intervals of the difference between all of those samples I showed you. And there, where there's a low p-value, the difference isn't 0.5, which I had posited originally. It actually comes out as greater than 1, and that's a pure chance finding. So it's very embarrassing when people write papers and say they found something significant with an underpowered test. They've often exaggerated the effect they find, and nobody can subsequently replicate it. And we'll be talking about that in the next hour. We'll be talking about this in the next hour as well. And there are lots of reasons why studies can't be replicated. One of them is the statistical one I've just explained. The other is publication bias, you know, that if it's not a significant effect, then people don't think it's too exciting. Another is confounding. You've had something which has interfered with your experiment that you've not recognized, and I'll talk a little bit about that in a moment. And the third thing is that you've not actually done it randomly, or you've not done it sufficiently well blinded to avoid bias. There's now a journal looking at whether studies can be replicated, and this is an example that's taken from, well, this isn't. This is the original study, but then they tried to replicate it and couldn't. And I love it because it's a really funny story. What they did was they took a sample of volunteers, randomly divided them to two halves, and made them write out a story. So the first half wrote out a story where, and it was written in the first person. And at the end of the story, the person writing the story did something really nice, really pleasant, really good for humanity. Whereas the other group had to write out a story in which at the end of the story they did something really bad, horrible, morally repugnant. What they then did was take those groups and ask them to rate their perceived value of a particular product, like Mars bars and things like that. And they rated them in terms of whether they thought they were good things or bad things. And the people who had had to write out the unethical story were much more likely to choose, they said, cleansing products, like they wanted to wash their sins away, than the people who had had the morally reasonable story. Well, that's the original illustration from the original paper. I don't like graphs which don't start at 0, and this actually doesn't go to the maximum either. So let's just replot this graph. There's the original. Here it is replotted on a categorical scale, actually, from 1 to 7. This isn't a continuous measurement. You had to give it a score of either 1, 2, 3, or whatever for this product. And then we've put on the numbers in the groups here, and you can see they're not very big. And if you replot this to show the 95% confidence intervals, they actually overlap. And when people tried to replicate this study, very much more carefully with a larger sample, they weren't able to do it at all. So, big danger in trying to tidy up your data too much. Someone will come along, possibly later on, and repudiate it. So what can you do about it? What have we got available in our armamentarium to properly analyze our data? Most of our data may be comparisons. Sometimes we're looking at relationships, such as a time series or a dose-response curve or something like that. And under those circumstances, it's very sensible to use the data as efficiently as possible. And I'll give you an example of how to do that in a moment. The other is to try to avoid assumptions about the population, because you can't necessarily assume that your populations are normally distributed. And there are very powerful tests nowadays, statistically available, which avoid having to make these assumptions at all. And then try to avoid any confounding. Try to be as random as possible. Don't take all your rats from the bottom left-hand cage today and the top right-hand cage tomorrow, because they might be different. One group might be sleep deprived or something like that. You don't know. So this sort of summarizes all of statistics on one slide. Your comparisons may be of continuous data, continuously distributed data, in which case the t-test or the Wilcoxon test or something like that is a thing to use. They may be categorical, yes or no, in which case you've got to use categorical non-parametric tests to analyze those data. Often, scientists are looking for interactions. In the wheat field at Rothamsted, which was the Agricultural Research Institute, their analogy was that there could be a wet end and a dry end, so increasing aridity or increasing moisture probably in this direction. There might be a shady side and a sunny side. So there are two different effects that are going to influence the growth of the corn, and there may be an interaction, and you may see the tallest corn at the moist and sunny side, sunny corner of the field. If you want to do that in much more detail, modelling is very useful, very sensible way of trying to account for several interacting factors. But before you even try to come up with any of these tests, just try to ask, what are we trying to show? What is the crucial point of the study? Don't keep on just throwing p-values at it and t-tests at it. Decide the central message and concentrate on that. Looking at the more modern tests, the permutation test says, okay, you've done 8 tests, 4 in this group and 4 in that group. Could there be a difference between these two groups? Could I rearrange these numbers in any more extreme fashion than they exist at the moment? The sort of analogy of the p-value, if you like, could these have been any more or less diverse than they are at the moment? And to do that, you rate them in magnitude and then pick out all the possible permutations of those values into these boxes. And that's, for small sample sizes, a very robust test. For slightly larger samples, the bootstrap method consists of taking a number of values in your sample and taking repeated subsamples from those. So subsample 1, 2, 3, 4, 5, and so on, to give you ultimately an estimate of the population that is completely doesn't require any assumptions about the shape of the distribution. I said I would come back to dose-response curves. My heart always sank when I got papers which showed times. Let's say this is a time series, day 1, day 2, and there's 2 groups obviously here. And what often happens in papers is that people painstakingly go through and they do a comparison between this lot and this lot, and they give you a p-value in here, and then, oh, how are we going to explain this? Well, I can tell you why it's happened. It's because it's random. It's just the way that those samples have fallen. But that's a completely wasteful and unnecessary way of analysing a set of data like that. Far better to plot a line through the whole lot and then see, could that line be the same as that one? And the answer, very frequently, of course, is highly unlikely. It might be even better to use a curve. If, biologically, that would make more sense. Another very serious defect is applying the test the wrong way round. We start over here with a single random, a single group of volunteers, let's say, or fish or something like that, we randomly divide them into 2 identical groups. If they're not identical when they've been randomized, there will be very small differences, but those differences are only due to chance. Then we apply treatments, A and B, and we get the results of these treatments applied to these random samples. What often people do then is to compare after with before. Now that is quite a powerful test to do because you've taken into account the variation that there is within this sample to begin with, but it's the wrong comparison. The true comparison should be between this, and then the only influencing factor will have been the treatment that's been applied. There are some ways of getting around the random variation of these samples using analysis of variance, but the point I'm making is that that is the only comparison that you're entitled to do if you've taken 2 random samples from your contributory population. The other very serious defect that occurs over and over and over again is pseudo-replication. Rats and mice are expensive. We're not supposed to use too many of them. So rather than taking a single sample from a mouse, we take 3 samples from a mouse. We take 3 samples from the next. And then it's completely erroneous to say that the sample number is 12. What you really should do is to mean those 3 samples, and then your n would be 4. The experimental unit is the smallest feature that is tested. Could even be a cage, or a class of school children, or a hospital even. You've got to remember that there is variation within the unit and between the unit, and that these are different sources of the final variance that is measured in the data. And this is frequently overlooked in physiological testing. The story that a colleague of mine told against himself was a very good example of confounding. He was interested in head injury, and he was hitting rats on the head. And it was supposed to be a non-fatal injury, but they all died. And he was really concerned that there was something going on, but he wasn't quite sure what it was. Well, what he was doing was dropping weight on the rat, and the rats were dying, not because of head injury, but because they became anosmic. He hit the wrong part of the rat, knocked out its nose. It couldn't tell the difference between food and bedding, and they all ate their bedding and died. So there is the story there is be sure that you've taken all factors into account when you're looking at the results. If you need a test, use the correct test. And quite often, the answer should be pretty clear. If you've deleted a gene and you're looking for the gene product, the protein or something like that, either it should be there or it shouldn't be there. There may be some sort of weakness in your assay which picks up other proteins other than the gene product, but let's hope that it's going to be fairly limited. And then when you look at the data and when you do a dot plot, it should be obvious. So the first robust test that I would suggest is, this is a barn, is the barn door test. If you can see it, it's likely to mean something, okay? And you might not necessarily have to prove that you're gene deficient and wild type animals are from the same bag, okay? And a modification of the barn door test is the Mark 1 eyeball test. Just look at the data, plot the data, and see what you get. Thank you.